Welcome, developers. If you are aiming for a senior engineering role, mastering JVM memory architecture is non-negotiable. Let's start with a foundational architectural choice. Why is the heap shared across all threads? The heap is the primary runtime data area where all class instances and arrays are allocated. By sharing it globally, the JVM enables efficient data communication. Multiple threads can read and write to the same shared resources, like database connection pools or caches, without needing to create expensive deep copies of objects across thread boundaries, saving massive amounts of RAM. If the heap is shared, why is the stack thread local? Think of execution isolation and thread safety. Each thread executes its own sequence of method calls. Thread A's local variables should never interfere with thread B's. By making the stack thread local variables are inherently thread safe without requiring any synchronized blocks or locks. Furthermore, stack allocation uses a simple last in first out LIFO frame pointer adjustment, making execution incredibly fast. Now, let's talk about where objects are born. Why do most objects start their lives specifically in the Eden space? This design leverages the weak generational hypothesis, which states that most objects die young, like local method variables or short-lived DTOs. Eden is optimized for rapid sequential allocation using thread local allocation buffers, CLABs. Because the JVM knows over 90% of these objects will be dead within milliseconds, it doesn't waste time cleaning them individually. It waits until Eden fills up, copies the few survivors elsewhere, and wipes the entire space in one fast operation. But why are there two survivor spaces instead of just one? This dual space design solves a massive physical bottleneck: memory fragmentation. If the JVM deleted dead objects in place within a single space, the memory would quickly become riddled with tiny, unusable gaps. By utilizing two spaces, S0 and S1, the JVM implements a copying algorithm. One space is always kept entirely empty. During a minor GC, the JVM copies only the live objects, compacting them tightly into the empty space. The spaces then swap roles. This eliminates fragmentation entirely without requiring expensive defragmentation sweeps. So, what exactly defines a minor GC? Also known as scavenge GC. A minor GC is the rapid cleanup of only the young generation, which includes Eden and the two survivor spaces. It is triggered automatically the moment the Eden space becomes completely full. Because it completely ignores the massive old generation, minor GC runs incredibly fast, usually finishing in just a few milliseconds with negligible impact on your application. What happens when objects survive multiple rounds of minor GC? They get promoted to the old generation. And when the old generation runs out of space, it triggers a major GC to clean up long-lived objects like singletons and static configurations. However, if the JVM needs to clean the entire heap, including both the young gen, old gen, and the metaspace, where class definitions live, it executes a full GC. Full GCs are heavy resource, intensive operations that freeze your application threads in a stop. The world pause to trace and compact all memory. To clean memory without destroying active data, the JVM must know where to start looking. It relies on GC roots. A GC root is an object that is inherently active and reachable from outside the heap structure. There are four primary categories of GC roots you should remember: local variables currently residing in any thread's active stack frame, live running Java threads, static variables attached to loaded classes, and JNI global or local references within native C or C++ code. How does the JVM actually determine that an object is garbage? Many developers think Java uses simple reference counting, but reference counting fails to handle cyclic references, where object points to B and B points to A, but nothing else uses them. Instead, the JVM uses reachability analysis. The garbage collector starts at the GC roots and traces every downward reference link. Any object that can be reached via a continuous path from a GC root is marked as live. Any object or island of objects that cannot be reached from a root is flagged as unreachable garbage and reclaimed. Since Java automates garbage collection, can an application still suffer from memory leaks? Absolutely. In Java, a memory leak is a logical leak. It happens when an application accidentally maintains a strong reference path to an object it no longer needs. The most common culprit is a static collection, like a hash map. Because static variables are GC roots, anything stored inside them will remain in memory indefinitely, unless explicitly removed. Other common leaks include unclosed resources like database connections, unremoved thread locals, and lingering event listeners. To give developers finer control over object lifecycles, Java offers 4 distinct tiers of references. First, strong references, your standard everyday object instantiations. The GC will never collect them as long as the reference path is active. Second, soft references. These are kept alive unless the JVM is running completely out of memory, making them excellent for caches. Third, weak references. The GC reclaims these during the very next collection cycle regardless of memory availability. And fourth, phantom references, which are used strictly to track when an object has been fully swept from memory, so you can execute post-mortem cleanup safely. Here is a brilliant JIT compiler optimization. Escape analysis. While we are taught that all objects live on the heap, the JIT compiler can actually bypass this rule. It analyzes a new object's scope to see if it escapes outside the method that created it. If the object remains strictly internal to the method, the JVM can perform stack allocation. This places the object directly onto the thread's stack frame, meaning it is instantly destroyed the moment the method finishes, putting zero pressure on the garbage collector. It can also break the object apart via scalar replacement or eliminate unnecessary synchronization locks. Finally, let's look at the biggest pain point in enterprise systems: long GC pauses. Why do they happen? And how do you tune them? Long pauses occur when the JVM stops your application threads. Stop the world event to clean or compact a large fragmented old generation. This is frequently driven by premature promotion, where a small young gen size forces short-lived objects into the old gen too early. To resolve this, always analyze your JVM unified GC logs and inspect heap dumps using tools like Eclipse Mat. By tuning your generation sizes and adopting modern concurrent collectors like G1, GC, ZGC, or Shenandoah, you can shift compaction work to run concurrently with your application, ensuring ultra-low latency. Let's do a quick, high-level summary of everything we covered today. We started by looking at memory allocation layout, understanding why the heap is thread, shared for instant data communication, while individual thread stacks are kept local for isolated execution safety. Next, we journeyed into object lifecycles, showing how the Eden space uses T-labs for lightning, fast object creation, how dual survivor spaces use a copying mechanism to completely eliminate physical memory fragmentation, and how minor GCS target just this young tier in milliseconds. From there, we scaled up to the old generation, contrasting targeted major GCs against massive global full GCs. We unmasked how the JVM traces live references down from active GC roots using reachability analysis, instead of fragile reference counts, and why forgetting to clear references out of static collections leads to logical memory leaks, even in an automated runtime. Finally, we covered advanced optimizations. We broke down the 4 tiers of Java reference strengths from strong down to phantom, showed how JIT escape analysis can dynamically bypass the heap altogether to perform ultra-fast stack allocations, and looked at how premature promotion triggers the long stop, the world GC pauses that stall high-throughput systems. When you tie all 12 of these pieces together, you stop just writing code blindly and start architecting highly optimized production-grade applications. If this structured deep dive gave you a clearer understanding of how the JVM operates under the hood, make sure to hit that like button, subscribe to the channel for more advanced architecture content, and drop a comment below, letting me know which of these concepts you want us to build a full code demo for next. Thank you so much for watching. Keep building high-performance systems, and I will see you in the next deep dive.